Hello, everyone. Thank you for having me here today. I'm Dr. Levin. I am from Mount Sinai Health System in New York, and I'm going to talk to you today about very practical level of what I've done, what we've done for the past 2 years at Mount Sinai to try and bring some of these technologies and innovations actually into the hospital. So my background, I studied computer science at MIT and then went to medical school, eventually did anesthesiology and then cardiac anesthesia. So I'm a practicing cardiac anesthesiologist, and for the past 2 years I've been building a data science team. Mount Sinai is a 1,000-bed hospital in New York City on the Upper East Side. I didn't put any pictures, which about 6 years ago bought several other hospitals throughout New York City, so is now about an $8 billion enterprise with 5 or 6 campuses, and we're trying to build solutions that let us deploy models on those campuses. So I don't have any disclosures. This is a US-based talk, so I always have to say no disclosures. The agenda, I'll sort of talk about why we thought we needed to build something that was outside of the box of the EHR, what the architecture is of what we built. So unlike Eyal's talk, this will be a little nitty-gritty, and then present you 2 use cases of models that we have running. Okay, so why do you need this? Well, everybody knows there's lots of data in healthcare. The problem is that the EHRs as they currently exist are not well equipped to do any sort of real machine learning on this data. They don't have the tools, they don't have the correct architecture, and performance-wise, machine learning can be expensive, so you can't run models on this. So what was the idea was to let's build a platform that lets us take models that you would develop historically. So most academic medicine is you build a model once and then you forget it. You publish it and you never do anything with it again. And you don't even know actually if that model is validated 5 or 10 years from now because nobody validates anything that they publish. So our idea was, well, we want to actually build something where we can build a model but then run the model and use the model. So we did this locally, and I'll just touch on this briefly, that why do we do local versus the cloud? Because everyone always asks me, well, why didn't you just build it in AWS or Google Cloud or whatever? The answer was really just because I didn't have the expertise. No one had the expertise that worked for me. And the questions were unanswered of what is the true cost. So if you're running something 24 hours a day times 7 days a week times 52 weeks a year, cloud computing is actually quite expensive for that use case. And the local is competitive. So I could spend $50,000 on local hardware, or I could spend $50,000 for 2 months of cloud time. And then there's always issues in the United States of privacy. We heard from John Halamka this morning that in China they don't care about privacy, but in New York they really care about privacy. So everyone wants to know, are you HIPAA capable, HIPAA compliant? Well, you could go to Google or Amazon and they'll say, well, we're HIPAA capable. You say, what does that mean? They say, well, you can make a HIPAA compliant platform on our platform, but we don't make any guarantees. It's all on you. So if I'm going to do that, I might as well do it myself where I can control everything. So what did we do? The first thing we did is build a cluster. And again, I said this was going to be technical, so I'll try and go through these quickly, but hired a bunch of developers, smart guys, and they said, we like Mongo. I said, great, fine. So you build a Mongo cluster. Okay, so that's your data lake, if that's the term that everybody likes to use now. But the key is that this is the scalable, replicable platform that you can use to drive all the subsequent model building. And then you have to build something on top of it. So this is the tricky part, actually, which people get all excited about building sexy models, but you actually have to build something to run the models upon. And the problem is, in the large health system, and Eyal alluded to this a little bit, there's dozens of systems. Mount Sinai has, I think, 35 clinical systems. And even if they try to consolidate most of the documentation systems to one platform, which is Epic, you still have laboratory, billing, pathology, radiology, EKG, and that's not even talking about waveform data, streaming data. So you have to get all these data. And the lingua franca, and I don't have it here, is HL7. And again, Dr. Halamka referenced this morning, fire this, fire that, it all sounds great, but the majority of healthcare data still flows around as text data, pipe delimited HL7 messages. So you have to get it all in. Mirth is a freeware HL7 platform. So you can download this from the internet and you can fire it up and you can start processing messages and writing transformations. And then you stick it into a database here. And this database has replication and it has security and the logs are encrypted and everything, data at rest, data at motion, it's all private. And now you want to do something with it. So you have a message streamer that takes messages, listens here, takes data, and sticks it someplace into Spark. So Spark is sort of like Hadoop, but in-memory processing. So you can run jobs. And I'll show you in a second a slide of our Spark dashboard. But you need to do something with all these data. And if you were sitting on MD Clone demonstration earlier, it sounded suspiciously familiar. So you want to make what's called a full story. So the patient comes into the hospital, and they get some labs, and they get some tests, and they have a note written, and a nutritionist sees them, and a speech and swallow therapist sees them, and then they get a consult for nephrology, and all of these things, you can put them together into a timeline of their stay inside a hospital, and that becomes the basis for your analyses. And then you want to do analyses. And so here you do something. And again, I hired a bunch of guys, and they said, we like Scala. And I Googled Scala, and it's Java-based, and it's great for machine learning. So I said, fine. Maybe the downside is that not too many people actually program in Scala. So maybe this would be better with Python, but whatever, it doesn't matter. The point is that you do some learning, and you make a model. And now your model generates a prediction. And I think the most interesting part of all of this is that what we have done is we've tied this prediction back to the clinician. So the prediction goes into Mongo, but then the prediction goes back, and this is the dashed line, and the prediction flows back to the EHR. It flows to a care team and gets a mobile notification. It goes to a dashboard. It goes to performance reports. So it all lives there, but it all actually goes back. All right, so now just a quick few slides so you can see. So the nice thing when you use open source tools and you use things that have been built in the industry that are best of breed is you get all these great dashboards and reporting for free. So here's our initial database, and we have 0.5 terabyte of data, which is really not very much, but that's what we started with. Here's what's going on in the database. Now here I talked about Spark, so here you see, and this snapshot I took, I think this was early March, and it had been up for 3 weeks. It had run 80,000 batches. So every time a piece of data comes in, generate a prediction, send a prediction to the EHR. And you can just watch. And does this mean anything right now? No, but it means that when we start to run 2 models, 5 models, 10 models, 20 models, and we wonder why their performance is lagging, we can look and we can understand what job is lagging, where the bottlenecks are in our performance. So this is all very important systems engineering that if you're building machine learning platforms, you have to do this, and Google does this, Facebook does. If you can go and look on the blogs for any of these large internet scale platforms, and they're full of this stuff. This is what they do. Okay, so use case 1. So now we talk about the interesting stuff to the clinicians in the room. Inpatient malnutrition prediction. So someone earlier today asked me what malnutrition is, so because maybe it's not a familiar word, but malnourishment is the state of being underfed for your calorie requirements. And this can impact your recovery from illness, for example. It impacts your strength. It impacts your quality of life. Okay, so there was a case here where Mount Sinai had noticed that relative to its peers, its documented rate of malnutrition among its inpatients was low. And so not only was this affecting patients and morbidity and mortality, but it also affects our revenue, and it also affects our rankings, because the U.S. is all about rankings. Colleges are ranked, hospitals are ranked, people are ranked, everybody's ranked. So we're below our peers. So now if you're an educated consumer shopping for healthcare, oh, why would I go to Mount Sinai? Because they're lower ranked in this category. Okay, fine. So previously what had happened, so you have someone called a dietitian. Here it's RD, so registered dietitian. This is a person whose job is to go around the hospital and interview a patient and say, what are you eating? Are you having breakfast? How many calories? And then they estimate based on their weight, age, BMI, how many calories they need. Are they in a highly metabolic state, like they just had surgery and they're stressed? So are they a catabolic, anabolic, whatever? And ultimately come up with a label, and this is very important for learning, is a label: malnourished, yes, no. And it was being done in an ad hoc fashion, so there were not very many dietitians. They would kind of go where they were called. They wouldn't see people in a systematic way, and we thought we could do better. And the way we thought we could do better was predicting which patients were likely malnourished, and then giving the dietitians a list and say, go see these patients first, because these patients will have higher yield than if you just randomly sample patients. Okay, so model development. You start with a batch of historical data, and you have a gold standard, a label, which is this patient was malnourished, the dietitian said it, and you train it. And we started with random forest because random forest seems like it works well for medical models. And relatively small batch initially, so only 14,000 patients, which sounds like a lot, but is actually pretty small. And 6,000 unique admissions among these, so it's tiny. And then you do all the things that you do. And then you do a validation set, a training set. You undersample because the rate of malnutrition is low. So your classes are going to be imbalanced, and you're going to overfit or underfit. And you get a model. And so we got a model. Ended up being only 2,000 patients, right? Malnutrition rate of 12.6%. Sensitivity, specificity, area under the curve, pretty good. Looks like a good model. Okay, now the interesting stuff starts, which is that you have to take this model. And so just to go back, you take this model, and now you have to have what you develop in batch has to be translated into Scala or Python or whatever that can actually run on a stream. So streaming models are very different in terms of the way they use data. And I don't even talk about that here. So you deploy it. So we deployed it to 2 floors. And throughout this all, the other very, very important piece was that you have to work with your clinicians, in this case, the team of dietitians. So you have to get buy-in. So I personally wasn't involved with this, but my co-director, who's a operations director for the hospital and has a nursing background, he met with them every week to get buy-in, to say to them, listen, we're going to try and make your workflow more efficient. We're going to try and get you to see the patients that you should see and not just random patients. And what do you need, and what's the workflow that you need? So we did this, and then we rolled out to the entire hospital in October. And then in Q1, so around January, February of this year, we rolled out to 2 other hospitals, and now we've rolled out to a third. So now we have 4 hospitals. And one of the things was that in this model, you develop a threshold. So you know, what predictive threshold, and we ended up that the threshold was 0.55. It doesn't matter what the number is. You tune it. You choose what threshold you think gives you the best F1 score or the best accuracy or whatever parameter you think should be most optimized for this use case, and that's what you use to generate the prediction. And now this is the interesting part. So this is a snapshot from Epic, for those of you who may not have seen it. This is kind of a typical Epic screen, so you have all these units over here and a header and lots of stuff, and then you can make patient lists, and then right here, this we pushed into Epic. So this never existed before, and we created a data element, and we push every 5 minutes a prediction. So one patient will have multiple predictions, and when you hover over this prediction, you get a score, and that score tells you the top 10 factors that contribute to that score. So in this case, albumin is 2, which is low. Hemoglobin is borderline. Creatinine is a little high. PT is a little elevated. The lactate is elevated. Okay, this person has a high. So now the dietitian, they start their day, they look at this list, and they go see the patients. So what happened? We rolled this out. So to back up a few seconds, we started somewhere down here. The hospital, Dr. Rich, who's here as the co-chair, hired 20 more dietitians and got us to here. So just by having more people running around, you know, human engineering is very important. And then we roll out here, and now 3 months later we're here. And this is our peers. So we're now exceeding our peers. We have a 500% increase in the capture rate of malnutrition. The patients haven't really changed. The same patients are coming to the hospitals, right? But we are now better capturing a condition that affects their morbidity, mortality, and potentially improves our revenue. And I won't even talk about that part. Okay, so now here's the other thing, though, is that when you deploy a model that's been trained on a small batch data set, you see this. You see that streaming, historical, and must is a manual score that the dietitians use, which is highly specific, but not very sensitive. But you look at our historical model, and it was fairly balanced. We deploy it, and suddenly the sensitivity plummets. So we start getting lots of false negatives. We're missing patients. Why? Because we trained on a relatively small set. Okay? But now what's the beauty of the way we've designed our platform is that we're capturing all these streaming data. So now we can start to retrain our models. Okay? So now we're in the process of training version 2.0. And we have a random forest, a gradient boost model, an ensemble model where the models vote. And you can see that all of them actually perform better than the first model. All of them have AUCs that are comparable to what we saw in historical, and we've now boosted again our sensitivity. Now you have to choose here what you want, right? And which is most important. Is it most important to not miss anybody, or is it most important to not fatigue the clinicians by sending them on wild goose chases to see lots of people who are not malnourished? Which will bring us to another point that's important that I'll talk about. So I'll talk about it here because this is the last slide on this, which is calibration. So we do these models and we see, okay, we can improve the performance, but is the model calibrated? When we say that there's a 50% chance that the patient is malnourished and the dietitian walks over to their bed, is there actually a 50% chance that when they walk in the room that the patient is malnourished? And so for that, you have to calibrate the models. So we just actually deployed a calibrated, we're testing a calibrated model based on this version 2 off of the streaming data, and so on and so forth. So we can iterate now rapidly because we have a platform, we have a set of APIs that we've built internally. We can develop a new model and then we can just deploy it. And I could talk later if people want about the deployment tools and the way you package up software to deploy it. But again, best practices from the internet industry, from the software industry, and bring them inside. The second use case I'll talk about is early warning. And this is now talking about, can we prevent patients from deteriorating in the hospital? And we call it Muse++ because there's an old medical score. The early warning score was 4 vital signs, pulse, heart rate, respiration, level of consciousness. Then people came up with modified early warning score where they added some stuff. All these were still manually annotated scores. So we said, well, why don't we try and develop an automated score? And we're not the first people to do this, but again, where we're trying to innovate is by deploying this as an actual model that runs. So I won't spend too much time on this, but I'll just again go through that, start with the historical data, build a random forest model. Now in this case, we're using a lot more data. So this is actually a much bigger set because now we can use every patient who came through the hospital for the last 5 years and say, did you deteriorate or not? And what was the unit that we looked for of deterioration was actually escalation or transfer to a higher acuity level bed. So it's very hard to look at historical data and determine how did a patient escalate, what intervention did they get. But if you look at bed movements, you get a rough proxy of it. How much time do I have? 5 minutes? 3 minutes? Okay, so I have 3 minutes, but it's a very similar story to what I showed. Build some models, see which works best. Again, it seems like random forests work best for medical applications. If you read the literature, this seems like the literature agrees with this. Now, our goal was to predict in advance. So here we have time prior to the escalation. So again, escalation is you were in a floor bed and you got moved to an ICU. Okay. So this blue line is the automated model, and this is our recreation of a manually scored Muse model. And you can see that they start out pretty close, but the further you get out prior to the event, the worse the classic Muse performs, yet we stay almost the same. So this is very exciting because potentially you can predict 6 or 12 hours before someone's going to deteriorate and you send someone. Okay, so again, generate a score, stick it in a thing. Here we say not for clinical use because we're not ready to use it yet. And how do we pilot this? So I put this up not because I want to walk you through this, but just to show you that when you go talk to the business process engineers and you say, well, we want to, on 2 units, design an alert that's going to replace the nurse calling the rapid response team, what is involved in trying to do that? And it generates this enormous process flow chart with decision trees and this and that, and then you have to think about alarm fatigue, and am I going to generate 6 alarms in one shift, 10 alarms in one shift, 20 alarms? I don't know. We're still figuring that out. So we're about to roll the pilot, and then very important is to make these dashboards. So this is just a snapshot of a dashboard written in Python and Plotly, because you want to be able to communicate to your users, how are we doing for you? And you want to be able to communicate to the nurse managers. And notice that a lot of these things, we're not even really talking about the doctors. We're talking about all the other providers of care in the hospital. Because the doctors are busy filling out Epic forever. Like, that's all doctors do. and not me because I take care of patients in the operating room, but on the floor, you spend a lot of time charting. So here we have just simple charts. We're trying to show, okay, how many patients were medical versus surgical? Okay, in 12 hours, 8 alerts were generated on medical patients, and I don't even see the number here, but 7 on this. What types of alerts were these? So this is now on top of the model, which generates a prediction. You've now placed a heuristic algorithm that's going to send alerts to patients. And so you're trying to evaluate the workload. So, okay, in 12 hours, if you get 3 plus 2 plus 3, that's 6, 8, 10, 11, 14 alerts over 2 units. And if there's 8 nurses a unit, you can do the math. I mean, is this a sustainable workload for the clinicians who are going to use this? Because if it's not, there's no point in doing it. Nobody will use it. They'll turn it off. They'll ignore it. And you won't have improved care. You'll just have spent money. So we're in the process of doing this. So in conclusion, I would say that the EHR systems that are available, as was alluded to many times today, they are not made for this type of analytics or this type of prediction. They're charting systems. But outside of healthcare, there's very rich and deep technology stacks that are made for predictions. You look at your phone, when you pick up Google, Google says, I think you're near this place. I think you would like this restaurant. So the technology is there. So you just have to bring it in. And when you bring it in, I think you can build very interesting applications.